Alrighty, now last day we basically learned how to do this. Major deal. We did e to the x. Is e to the x the only exponential function that exists? I think it isn't. Right, we talked about, the bacteria in the petri dish doubling every 4 hours. Well, that would be a 2 to the x, right? If I'm talking about things involving, let's say, pH and things like that, that would be 10 to a power. So clearly, e isn't the only base. It's just the most convenient base because the calculus of e is simpler than the calculus of anything else. Here's the thing. Here's what I'd like to do. Let's suppose A is not E. Let's suppose A is 2, or 10, or 3, or 5, anything else but not E. It makes perfect sense to ask, what's the derivative of this function? Well, how would I get there? This is always true. If you remember from going back in your algebra days, to undo a log, you exponentiate. To undo an exponential, you do the log. So if you do the exponential of the log, they're inverses. They undo each other. Now, the f of x has to be positive because if I take the log of a negative number, well, if you do a log of a negative number on your calculator, it's going to say error. It's because the log of a negative number is imaginary. Now, we can't manipulate that. But if that's the case, then if I have a to the x, how can I make that work for me? Well, then that means that this would be e to the natural log of a to the x. Okay, this is absolutely always true. Why is this good? You guys know what's coming. This is now e to the x log a. A is a constant. Therefore, log a is a constant. Off to the side, if I asked you to differentiate e to the 3x, what would you tell me the answer is? Wouldn't you say e to the 3x times 3? I want you to differentiate this. But if log a is just a constant, then wouldn't the derivative of e to the x log a be e to the x log a times, what's the constant? Log a. But wait a minute, what's e to the x log a? Isn't that just a to the x? Isn't that where that came from? So what have we got?
Log a.
That's it. The derivative of a to the x is a to the x times an additional log a term, which is a constant. Now let me throw a what if at you. What if a actually is e? What is the log base e of e? 1. So if that a actually was e, then that right there would equal 1. And we have the other formula anyway. So in other words, it's more of a whew. It still works. So I would like you to differentiate, 10 to the x. Let's keep it simple. So the answer should be 10 to the x. And then that's it. That was pretty easy. Now, that's the x, but we saw all of our derivatives really need to be in the chain rule form. So the question is, what if it was this? Not a to the x, but a to a function of x. Same rule applies. It's still going to be a to the u. It's still going to be log a, but now I have the chain rule factor that looks like that. And you notice every single one of your derivative formulas, especially if you have the sheet of derivative formulas, do you notice that every single one of them ends with a du dx? Because every one of them we're using u as our argument instead of x. We're using function of x instead of x. Then if my function of x actually is just x, then the chain rule factor is just 1. And it's safer that way because you say, okay, I've now covered every conceivable case that I could possibly run into. So let's do another one of these because these are fairly simple. I would like to differentiate 6 to the tan x. Well, that was kind of scary. Well, if I don't get anything else right, how about that to start with? Is that a good starting point? I'm differentiating 6 to the thing. So at some point I have to differentiate thing. But that's not an e, so what must also be here?
Natural log of 6.
6. I still have never differentiated the tangent function, so what else?
Secant squared x.
Okay, now what?
I think that's
Now
it.
is when you wave at it as you're walking away, you're done. And I always say that. Today in my Calc 3, they were learning a new form of differentiation. It's called partial derivatives. It's what happens when you have multiple independent variables. And every class they kill it. But early on, it was a little tough because they'd never done it before, and so I'd say, what next? And usually, so we want to do more stuff, and other folks would say, I think we're done. That's the right answer. We're done. There's nothing else to write. Now, is there anything wrong with the form of this answer? Do I need to rearrange things? Well, in theory, this is a coefficient, so where should this go? I should still put it in front, but I would always leave parentheses around it, so there's no way I can confuse it. Here's the problem we sometimes have. Okay, if I said cosine xy, if I said the natural log xy, same idea. Is the argument xy, or is the argument just x, and I'm multiplying everything by y, or is the correct answer, I can't tell. See, this is horrific. This is horrific, and all your books will do this. Both of these are terrible representations. The very fact you're saying, I'm not sure if you're asking me to do this or if you're asking me to do this. If you were asking me to do this and I didn't put parentheses, guess what all computers and calculators are going to do? Order of operations. Function precedes multiplication. Oh, so if I don't put parentheses, it's actually this automatically. But if I want this, where should I have put the y in the first place? So there's no ambiguity. And if I wanted this, I need parentheses. So you can't have ambiguity. So, well, where would the ambiguity come from? Am I taking the log of 6 or am I taking the log of the product, or is the correct answer can't tell by the way I wrote it? I guarantee you, everybody in this class, if you were taking the log of the product, you would have written it this way without parentheses. You have to have parentheses if there's more than one thing. Calculus people, for some reason, I don't know what it is, but they absolutely believe there's a worldwide shortage of parentheses. So you're on parentheses conservation. You know, it's good with water to conserve. But they found this cache of parentheses near Prudhoe Bay in Alaska where they found all the oil. They found this literally unlimited supply of parentheses, and they're free. They were left here, I think, by aliens. So we're never going to run out of parentheses, so never be afraid to use them. When you have an operator acting on a product and you don't put parentheses around the product, you're making it intentionally ambiguous, right? It's not always good. The reason I'm putting parentheses around the log 6, because if I don't, it's not clear whether this is part of the log or not. Because if it was part of the log, most people don't anyway. Same problem of ambiguity. I'm not sure what the intent is. Err on the side of putting parentheses even if you don't know if you need them. Because it's never wrong to put them in, but leaving them out could create a situation where you're not sure. Now, if I can take the derivative of any base raised to a power, we learned how to differentiate the log base e, or natural log of something last day. Wait, but in chemistry you don't usually use natural log, you use log base 10, right? What if I want to take the derivative of log base 10? I want to find how fast is the pH balance changing because something's going on. That actually is a chemistry problem. Probably a higher level chemistry. You're going to have to do rates of change of pH, let's say. That means I have to differentiate something that's a log base 10. Do you see the potential problem there? It's not the same as log base E. Well, last day I reminded you of something that you learned in baby algebra. This is always true. We call this the change of base formula that you learned in remedial algebra. And the reason we learn this in baby algebra is because very few calculators have the ability to do a base other than E or 10. The 36X Pro does, but I have a 89 titanium. I'll just keep telling you that. And I can't do a base other than E or 10. With powerful graphing calculator, I can't do a base other than E or 10. So that's why this formula exists. Well, that's one of the reasons. That's not the only reason. I would like you to differentiate the log base A of X and assume for a moment that, again, A is not E. Oh my gosh, how the heck am I supposed to do that? Using that formula. That formula was created so people could do things on their calculators when they had other bases. But it's actually real uses for calculus. It's so I can take derivatives of things. And the calculator is meaningless at this point. Can you rewrite this using the change of base? What goes on top?
X.
Well, very specifically,
Natural log.
of X. What goes on the bottom?
Natural log.
Natural log of A. But isn't natural log of A a constant? We just did it a moment ago. Isn't log A a constant? So could I literally do this? Are these equal? Stare at that for a moment. You just said log A is a constant, so can I pull it out of the derivative? Yes. But we know the answer to this. What is it? Then just 1 over x? So what's my answer? 1 over log A times 1 over x. Oh, the log A shows up in the answer again. But how does it show up differently? In the exponential, the log A shows up as a product. In the log, it shows up reciprocal. That's actually quite important. It shows up, but in a different spot. So I can differentiate any base. I just have this additional term. And then once again, I'm going back to this problem. What if A is actually E? And it really is the natural log that I'm differentiating? Then that's a 1. So again, we're covered. So, last piece of the puzzle. What if it's not just an x? I want to differentiate the log any base of u. Well, think natural log first. So shouldn't my answer be 1 over u times du dx? That's what I would do if it were a natural log. But it's not natural log, so what else do I have? That guy. That's it. Now, I mentioned this last day. That's the formal formula. What if your chain rule factor is just one term? What if your chain rule factor is just one simple term? Rather than write that as a product, could we just stick this in the numerator? That's what we did last day, in case you forgot. But if my chain rule factor actually is a quotient, it's easier to write it side by side. But what if my chain rule factor is one term? Let's do an example of that. So according to the rules, I'm going to just go ahead and start off with the log. Okay. Now, the rest of the problem, I can pretend it's natural log. So won't it be 1 over secant? 1 over secant times the derivative of secant. Can I just put the derivative of the secant right here in the numerator? Mm-hmm. So it does not matter, but can I just stick it in the numerator because it's not a quotient? What's the derivative of the secant?
Secant tangent.
Or I write 1 over this times secant tangent, same thing. So my answer? You can't, the log term you're never going to be able to simplify because the log's an irrational number. So it's just always going to be some ugly coefficient in front. Don't worry about it. But that derivative was not hard to take. It's a fairly simple formula then. So we derived e to the x using limits. the derivative. We then did the log by using implicit differentiation. Now we've done every other base, a to the x, not by limits or even implicit, but by just using a simple identity, which is actually really, really cool and really, really powerful. Okay, so far so good? So now I'm going to show you some techniques. You could call them tricks if you want, but they're techniques. If I had a problem that didn't even involve logarithms, sometimes using logarithms can make it easier. So you remember last day I showed you the factorial. If I had to do a really large factorial, we can't, technology-wise. Okay, let's suppose we're in the future and now our computers can handle a really big number factorial, but we still have an upper limit. What if I want to keep going past the biggest number you can think of? Well, doing the log of the factorial meant that I did the sum of the logs, which is not going to be an outrageous number, and we figured out a way of doing it. So taking the logarithm when one wasn't necessary. So if I said I have y equal f of x, and let's say there's nothing log-ish or exponential in any conceivable way about this question. Is the following statement true? As long as f of x is greater than 0, this is true. By the way, it's true always, but I can't do anything if it's negative because it would be imaginary, so don't worry about that. I now want to take the derivative of both sides of this. Well, let's do the right side first. If I differentiate both sides, then won't this be 1 over f of x times the derivative of f of x? Well, how about if I just write f prime of x right here? What's the left side? This is going to be a very common step. Won't it be 1 over y
dy dx.
times dy dx? My goal in the problem was to find dy dx. So if I multiply both sides by y, then I have dy dx equals y times f prime of x over f of x. Now this sounds redundant because aren't y and f of x the same thing? They would cancel. I'm not saying this is how you do derivatives. I'm showing that if I ever do a derivative by starting by taking the logarithm of both sides, I will eventually get the final answer, and I will get it correctly every time. So I'm going to show you several examples of this, and then I'm going to show you times when this will actually make the problem, it'll actually make the problem faster. All right, so just a moment ago, let's say 6 to the, I think we did one like this a moment ago. I don't remember if this is exactly the same one. It's similar to one we just did. I know there's a formula and I can do this right now. But just for the heck of it, I like to use the logarithm. This is what is called logarithmic differentiation. This sounds confusing. If I said differentiate, I'm going to give you a problem with a logarithm, differentiate it. Great. I didn't do anything to it, I just took the derivative. This problem does not involve a logarithm. I'm going to introduce a logarithm. So this is called logarithmic differentiation because I'm introducing a log and then taking the derivative. So the first thing I'm going to do is rewrite the problem as the, okay, that's not red. Okay, I'm not good with colors, but I know that's not red. Try that again. So is this a true statement mathematically, what I just wrote? Yes. So now what do I have? I have the tangent times the log of 6, or if you want, the log of 6 times the tangent. Log of 6 is just a constant, is it not? So right now I've got the log of y equals this. I haven't done any calculus yet. Now let's take the derivative of both sides. So on the left side it's going to be 1 over y times dy dx. On the right side it's going to be the log of 6 constant times the derivative of the tangent function, which is what? Say it loud. You're right. Secant squared of x. I want everyone to hear your incredibly cool answer. Okay. So far so good? Now we're done with the calculus. My goal was to figure out what is dy dx. if I multiply both sides by y, now I'd have dy dx equals y times log 6 secant squared x. And I'm done. Oh, but I really don't want a y in my answer. What do I want to do? Replace it with that thing. And isn't this exactly what we did earlier? It's not the same answer? Now, was this a faster way of doing this problem? No, we have a formula. We could have done this in one step. The point was we got the same answer by doing the logarithm. That's what I'm trying to illustrate. In this problem, no, it's not faster. I have a formula that says when I want to differentiate this, this is the answer. That's why I'd rather you do that. It's a little faster. So why would I ever do this? Because I can use log properties. So let me show you something. You like this. All right? Does this look familiar? I want to take the derivative of this. We've done this before, haven't we? In your Wayback Machine, about, maybe 3 lectures back, we did problems just like this. And what did we do? We did product rule, and within the product rule, we did the chain rule, and then we factored and we gathered terms. It wasn't terrible, but it was, there was a little bit of work involved. You guys remember that? What if I said, let's use logarithmic differentiation instead on this one? It's not better, it's just different, but we're going to see something that we may not have seen otherwise. So if I take the log of both sides, and yes, I absolutely need parentheses because I need to ensure which part's within the log. Isn't the log of a product the sum of the logs? Do you agree with that? Wait, but isn't the log of something to a power? Do I get to bring those in front? Yes? No? Maybe? So now what is this? I haven't done any calculus yet. This is just the log of y. I now need to differentiate both sides. But differentiating the right side is going to be really fast, isn't it? Not a whole lot to do. There's no product rule. So, when I differentiate both sides, the left side will read 1 over y times dy dx. And by the way, I could write 1 over all of this. That's correct. I'd rather write 1 over y. It's less.
You started with 1, but now it's 4. 4x plus 1, you're at 4x plus 1.
Did I? Oh, thank you. You're right. I just can't read my own writing. That's a 1. Thank you. Yeah. Standing too close to the board. Okay.
Oh, it still says 4 on the very lowest line.
Inflation, Numbers just get bigger over time, I think. Okay, I just differentiated the left side. Now let's differentiate the right side. So it's going to be 6 times that plus 4 times that. You with me so far? 1 over u. What goes in the numerators? The chain rule factor, the derivatives. So what goes in the numerator? The derivative of 3x squared minus 2, which is what?
6x.
6x. And what goes in the numerator here? 4. Okay, we are completely done with the calculus. We're not done with the answer, but we're done with the calculus. That's interesting. Now, before I continue, I think it would be in our best interest to write this as one quotient. So if I write this as one quotient, do you agree it would look like this? So that means, just like in baby algebra, I'd have to go 4x plus 1 over 4x plus 1 on this one, and 3x squared minus 2 over 3x squared minus 2 on this one. So let's put our new numerators in there. So I have 6 times 6x times 4, so that's 36, so that would be 144x squared, and then 36x times 1. And then here, it looks like I'd have 12x squared minus 8. Oh, no, I'm sorry. I lost a 4 there, my bad. Sorry. 4 times 4x, so that would be 48x squared, and then minus 32. There we go. Okay, so let's make this a little prettier. So how about 192x squared plus 36x minus 32 over 3x squared minus 2, 4x plus 1. Is the numerator factorable? Well, I know I can factor 192. I know I can factor a 4 out, but that's not important. Factoring a constant out doesn't change anything. Can I factor that as a product of binomials? I showed you guys a trick. Do you guys remember what it was? The discriminant? Is my discriminant a perfect square or not? Use your calculator. What is the discriminant? Tell me. See if we remember. It's a really big number. If this was factorable and you left it unfactored, you haven't finished the problem. But nobody in their right mind wants to factor that. Those numbers are too big. So you don't bother trying to factor it unless it's factorable. So how do you determine it's factorable? Find the discriminant. That's the b squared minus 4ac part. Does anybody have a number? By the way, I'm expecting you're all doing this because this is what you have to do. There's not a, well, I just choose not to. Well, then you're never going to have a right answer. You're going to have an almost answer. No, we want to be completely right. What's your, anybody have a discriminant yet?
28 times the square root of 33.
Say again?
I took the square root of it.
No, what's your discriminant?
Oh.
I just want to know if you got the right number to start with.
Yeah, I think so.
It's big. I'll wait. See, I could tell you the answer, but that won't help him. I really need you guys to tell me the answer.
25,872.
800 and?
72.
It's really big, huh? So the discriminant is 25,872, and you can all take the square root of that in your head, right? Well, no, now I hit the square root button. Now, the number on my screen is either an integer or it's not. Is it an integer?
No.
It's not. That means this has no, it's not a perfect square, so there are no rational roots. The only solution to this are 2 irrational numbers, which, by the way, if I needed to know, now I would just simply use my quadratic formula and tell you what the irrational numbers were. But if this were factorable, I would want to factor it. It's not factorable. You told that by finding the discriminant and taking the square root. That's it. And from beginning to end, that can't take more than about 15 seconds because there's not that many numbers. So that means, yes, I can factor a 4 out of the top. But I can't set 4 equal to 0, so therefore factoring 4 isn't really necessary. You can, you might not. Now, what do we got? 1 over y times the derivative equals this ugly thing here. Therefore, can I say the derivative equals y times this ugly mess? Is this true? But what was y? Y was one of the terms to the 6th power and one of the terms to the 4th power, and I have those same 2 terms here. Is something going to cancel? Oh, yes. How many of these are in my answer? How many of these, oops, how many of these are in my answer? And then that's what I have left over. 5?
3.
3, and there's my answer. The way we did it a few lectures ago, it was correct. We did product rule, and within the product rule, we did the chain rule, and then we factored out, and then we manipulated and gathered terms, right? We did a similar problem. But the route we took was very different from this route. Now, is this route an improvement? No, it's just another way of doing it. So why would I ever do a problem in this way? I'm glad you asked. I'll keep it simple. I'm going to make this really ugly. I'd like you to find the derivative of this. But you need to do it before October 1st. Are you excited to find the derivative of this? Oh my gosh. I think we all agree this is kind of ugly. A derivative exists. Would you agree this is pretty horrific? Well, can I write this as one product with everything being raised to a power? That would probably be wise. So how about if I rewrite this as 6x plus 3 to what power? 1/2 times 4x plus 5 to the third times 2x minus 1 to the
8? I think that's an 8.
Negative 8.
Negative.
which
Oh,
is
negative 8.
negative 8 and 9x plus 5 to the negative 1/3. Beautiful. Have we done anything yet? No, we rewrote the problem, but this is way better. Now let's take the derivative. So now we just have to use the product. Wait, the product rule is only for two things, isn't it? Anybody got an idea how I did the product rule on this? The fate of the universe depends on your answer. No pressure.
Break it into 2.
But it's like, how would I do product rule? I'll give you a hint. Here's one way. Make this my first function and make this my second function. First times derivative of second. Now, don't I have to do product rule within that? Second derivative. So I'm going to be using product rule many times. If I started in that corner, we might finish by that corner. It's going to be a lot of writing. Just say. Are you excited to do this problem? So let's say this was your admissions test to get into the university. Yeah, I'm just going to go to a different school, right? Can we do this problem? Well, I could say first times the derivative of the last three, but then within that product rule, when you have more than two functions, product rule is a little bit tricky because it's not really obvious. I have a really easy way to do this problem. What if I took the natural log of y? Stare at that for a moment. Do you agree? The log of a product is the sum of the logs, and the log of something to a power, the power comes in front as a coefficient. So yes, these are equal. By the way, are any of these individual derivatives even a challenge? 1 over this times 6, 1 over this times 4, 1 over this times 2, 1 over this times 9. I think we'd agree that's easy. So the next step when you do the derivative, your whole derivative is going to take you as long as it takes you to write. No time at all. The icky part is putting it back over one denominator, which I really do want to do. Because then when I multiply both sides by y, I use this version, I can cancel exponents all over the place. And we do know something. The exponents in my answer will all be exactly 1 less than these, won't they? So in other words, logarithmic differentiation on this problem will make this a small fraction of the number of steps it would have done to do it directly, if we even did it directly. So does that make sense why I might want to consider an alternate method? Because each of these derivatives is easy. The problem comes now in the simplification of combining things. That's a little bit of work, right? Putting everything over a common denominator is kind of a headache. Because we want our final answer in a factored form. What if you truly didn't care if your final answer was in a factored form? Then when you multiply both sides by y, the next thing would be the final answer. There wouldn't be any simplification, it could be done, but I'd have my final answer as a sum of things rather than a product. And we prefer products because then we can manipulate them, we can set them equal to 0, more stuff. But if I'm only interested in the derivative, not the factored derivative, the next step is the derivative, the next step is the final answer. You'd be done in just no time at all. So logarithmic differentiation is when you take the log of both sides and then you use log properties before you take a derivative. So what are the log properties here? Well, the log of a product is the sum of the logs and the exponent comes in front. Those properties make each individual derivative really, really simple to take. The previous problem that I did, this one here, when I did, you wouldn't use the logarithmic differentiation on that, you just differentiate it. No advantage to using a log, okay? So, let's try another one, you're gonna like this. We're going to look at the most challenging derivatives you will face in the entire semester. We're gonna do that one in a few moments. Let's see. Can I isolate the y? Can I isolate the y? Yes or no?
Well,
How would you isolate the y?
divide by x.
You have an e to the y on one side, you have a y cubed on the other. Can you write y equals and have no y's on the other side? No. Because you have two different terms with a y. If that were e to the x, could I isolate the y? Yeah, divide and cube root. But I have the, no, I cannot isolate the y. So the only way I can differentiate this is implicitly. No choice, implicitly. So we're going to d dx both sides. So this is sort of a reminder. This is what we're actually going to do. Because we're finding the derivative of y with respect to x, that means y is the dependent variable, so think of y as a function. Because you're not going to get a 1 when you differentiate y. So the derivative of the left side is? Good. I'm done. Product rule? So first times derivative of second.
3y squared.
Don't see y cubed, see thing cubed. So the 3 thing squared
dy.
times derivative of thing plus the second times the derivative of the first. 2x, that was easy. I only have 3 terms. You agreed that we should send this guy back? Then all my dy dx's are on the same side. Remember, our goal is to write dy dx equals. So if I can get all the dy dx terms together, then I can factor. So when I rewrite this guy, I'm going to have e to the y, put the 3 in front, minus 3x squared y squared, all times dy dx. See, I'm lazy. I put them together and I factor. On the right side, I'm going to have a 2xy cubed. Coefficient should always go up right. You can't have a coefficient in the middle. It's not a coefficient. Now, I got one more step. So dy dx equals 2xy cubed over e to the y minus 3x squared y squared. And everything I wrote is true and correct. Can I improve upon this? If I had to manipulate this, if I had to evaluate this at various places, you really don't like it, do you? That e to the y, certainly from an evaluation standpoint, definitely makes things harder, doesn't it? Do you agree with that? It's not easy to work with. Polynomial things are way easier to work with. Is there a way to write this without even having the e to the y in the final answer? Let me see something really obvious. Doesn't e to the y equal x squared y cubed? Any ideas? What's your idea?
It does. It does equal.
No, so I'd like to improve upon this answer.
Replace the e to the
Replace e to the y with,
x squared y cubed.
doesn't that sound, Oh, I won't have an e to the y in my answer. It'll be so much easier to look at. It'll make me so happy.
Oh, then you
But I'm
cancel out.
pretty easily pleased, so that's really not a thing. Okay, so far so good. Can I say absolutely that these are equal? Yeah, this is called substitution. I replaced something with something that's equal to it. Oh, might I be able to actually maybe factor and cancel something?
Mm-hmm.
I've got all sorts of common stuff top and bottom, don't I?
Mm-hmm.
I have an x in common on top, and I have a y squared in common on top and bottom. Now there's multiple paths. I'd rather be done in one step, rather. Okay, if I factor the top completely, I factor the bottom completely, then I cancel the common factors, and then I rewrite. All of that's correct. All that's correct. It doesn't matter what order you do things. But what's common right now? Isn't it going to be xy squared is what's common. Do you agree? If I do that, what will I get on top?
2.
What will I get on bottom?
X.
Minus 3x.
Can I factor that?
Yeah.
I can factor an x. So this is perfect. I think a slightly better answer would be that. Because then remember, bless you, it's not just where the numerator equals 0. I also need to know where the denominator is 0, because that potentially represents things like vertical asymptotes and just all around crazy too, you know. Look at my final answer. Now, was this answer correct? If you had to manipulate this, if you had to use this, you had to evaluate this at multiple places. You're in a physics class, maybe get 50 different times. This one. I don't know. I'm thinking that one might be easier. If I got to plug in numbers. In fact, the nice thing is, if I'm plugging in integer values for x and y, I'm not seeing integers. Excuse me. I'm not seeing integers here. I'm seeing integers, rational numbers there. I think we agree that one's better. So if we agree that's the bestest, mostest, coolest answer I can get, this was correct. We just happened to notice a common factor. Might there have been another route? You're nodding. Based on what we've done for the last half hour, what do you think the other route might involve?
Natural log both sides.
Take the natural log of both sides. Oh, that's 100 miles. That's easily 100 miles. Because I can see it, I can read it on their eyes. If I start this problem by taking the natural log of both sides, what if I told you we'll get the answer a lot faster? We're not going to get a different answer. We should get a different answer. That would be, well, that'd be wrong. How would I even know to do the natural log of both sides? Because I have an exponential function. Oh, and the right side being products, now I can use properties of logs. So let's go back to the original. E to the y equals x squared y cubed. You never have to use logarithmic differentiation. Here's a situation where you probably want to. Remember, the log undoes the exponential function. So when I log the left side, what do I have? Just y. But when I do it on the right side, it's the log of x squared plus the log of y cubed, so I can write it as 2 log x plus 3 log y. Oh my gosh. I've done no calculus yet. I just took the natural log of both sides, and that's what it reduces to. Now let's take the derivative of both sides. I think it's going to be a little faster. If I differentiate the left side, well, it's just dy dx. The right side, 2 times what?
1 over x.
1 over x, I'll just write 2 over x. 3 times 1 over y. Heck, let's write 3 over y
dy dx.
times dy dx. I'm done with the calculus. You with me on that? I have 2 dy dx terms, so I'll send that one packing. That's a 1 minus 3 over y. So I have 1 minus 3 over y dy dx equals 2 over x. Clearly, I want to multiply both sides by the reciprocal. It's not really in the right form yet. I can multiply both sides by 1 over all of this. Do you want to do that? No, how about if I made this one quotient first? Then it would be much easier, wouldn't it? How do you make this into one quotient? I'll give you a hint. Y over y. So y minus 3. So now when I multiply both sides by the reciprocal, what's the reciprocal of this? Same answer? Yeah. A little sooner? Yeah. Do we have to be clever? By the way, recognizing that I could swap this out, that was a major, major observation. Most people won't see that, and they'll leave this as the answer. And there's nothing wrong with this, but boy, it's a long way from that. This is correct, but it's far from being finished. I had to recognize I could swap out, and then all the algebra started from that point, didn't it? But if I had logged both sides, I'm starting here, and after one trip, I'm done with the calculus. Now I just gathered terms, and we got the same answer, but I didn't have to do any factoring. I didn't have to do any canceling. I didn't even cancel. Over there, at least we had to cancel, right? We had to be a little bit. So if we stop here, we haven't said anything wrong, but this can be greatly reduced. And we don't always see that. I didn't have to reduce this. It was already there. So I think we agreed no matter what you did, that's the final answer. Our goal is to get there as soon as possible, fewest number of steps. As I like to say, the least amount of pain and suffering. You want to be right, you want to know that you're right, but you also want to get there in the fewest number of steps. So in this case here, doing the logarithmic differentiation just happened to make more sense. You didn't have to. We didn't here, and we got the answer eventually, but it took us a lot longer. Plus we had to be a little bit clever, plus there was a bunch of algebra. And we know if there's a bunch of algebra, there's an opportunity we might mess up, right? I might make, in other words, a mistake. Bad factoring, bad canceling. Assuming you made no mistakes, it still takes a while. Pretty crazy, huh? So, logarithmic differentiation, you never have to do it, but having that in your tool belt, you're looking at a problem going, you know, I think this will be easier if I use logarithms. Okay? Now let's look at one of the scarier problems. Okay, reminder. This is always true if f of x is positive. Okay? Again, there's nothing wrong with taking the log of a negative number. It's just imaginary. And there's a whole branch of mathematics, and we're going to do a tiny bit of it in this course when we get to the hyperbolics. The hyperbolics, in case you didn't know, are the sines and cosines of imaginary angles. And the sines and cosines, strangely enough, cosine of an imaginary angle produces a real number, which is crazy. That's the only part of the 3 semesters where we even talk about imaginary numbers. Then when you get after calculus, you get to your higher level classes, you use them all the time. The problem most of us have is we have very little practice and even less exposure to the complex numbers in general, and then we get to the higher level math classes and we have to know it inside out. So your teachers are, rapidly trying to catch you up on complex manipulation. It can be a little bit scary. It's not the calculus, it's understanding the complex numbers, because in reality, everything's complex. Calc 1 and 2, you are mastering the calculus of real numbers in 2 dimensions. Both of those are woefully short. Why? Well, last time I checked, none of you live on a television screen. Right, you're not well, some of you are, but you're not cartoon characters. You live in 3D. So mastering the calculus of 2D is nice, but it's not very practical because you live in 3D, which means, hint, hint, you're never going to use the calculus of 2 dimensions in actuality. Most of you will be taking physics next semester, it's all 3D. Calc 3 is you now master the calculus of 3 dimensions, just taking what you've learned and extending it. And it actually, most people say they like that one the best because they're not really learning new things, you're just extending it. Now you've mastered the calculus of 3 dimensions. But there's of real numbers, but there's a whole world out there that's much, much bigger than the real world, and that's the complex world. So then you have to master the complex world. Differential equations, 255. If you're in this class, probably the case that you have to take that one. Now you start dealing with complex numbers and you realize you've been doing complex numbers your entire life. You just didn't know it. Because a complex number, anything of the form a plus bi, where I is imaginary, all numbers are complex. Sometimes the imaginary part just is 0. But it turns out, and I'll show you when we get to 255, if you were dealing with exponential functions, you were dealing with purely real numbers. If you're dealing with sines and cosines, you're dealing with purely imaginary numbers. Sines and cosines can only come from purely imaginary numbers. And if you're dealing with a combination of them, then you're probably dealing with complex numbers that have both real and imaginary. It's a very easy proof, but you got to wait till 255. You've been dealing with complex numbers your whole life. You just didn't realize it. You didn't call it that. When you were solving simple quadratics in baby algebra, remember you were doing factoring, and you said, oh, this is prime, right? Not factorable, no solution. No, that was always the wrong answer. There was no real solution. You may not have had real roots. All polynomials are factorable. Absolutely all polynomials are factorable. They just don't always have nice numbers. What do I mean by that? Well, I'm giving you a glimpse into the future, and the future in some cases is a little bit this semester, a little more next semester. If I said factor this, I think we're all okay. You agree? But your algebra books will say, you can't factor this one. I beg to differ. I don't know, I think it's pretty easy. I just don't have rational roots. And then, of course, you absolutely can't factor this one. Well, actually, you can. It's just as easy as the first one. You just happen to have imaginary roots. There's no such thing as prime if I'm talking about roots not having to be rational. Everything's factorable. There was no such thing as a no solution. There might be no real solution. And if the problem we're looking at, we're only dealing with real numbers, then no real solution might as well be no solution. But there's still going to be complex solutions. So we open up the doors and we extend things. And when we do that, it doesn't actually make things harder. In some cases, it opens up things. When we go from 2 to 3 dimensions, my Calc 3 class in a couple days, they're going to learn how to do implicit differentiation in higher dimensions. Sound scary? No. It makes it really simple. If you're in higher dimension, you go back and do Calc 1 stuff, it's actually simpler. It's not harder because you have more tools and you get to do more things. So here's an example of, we have artificial rules, we have artificial limitations. But when we're learning it, we usually are concentrating on the happy, easy stuff. This is always true. I would like you to differentiate x to the x. Let's see, if it's x to a number, I know exactly what to do. I bring the number down, x to the number minus 1. Agreed? If it's number to the x, then the answer is number to the x times natural log of the number. We just did that today. Does this fall into either one of those categories? I know variable to the constant, that's easy. I know constant to the variable, that's today, we just did that. This is variable to the variable. There's no formula, but I need an answer. And again, in Calc 2 on a regular basis, we have to save the world, on a regular basis. We do problems all the time in Calc 2. We will do problems where there actually is no answer, and then we'll answer it anyway. There's an infinite number of questions that have no answer, but you learn how to answer them anyway. That's Calc 1, you answer all the things you can't answer. Calc 2, you answer all the things that have no answer. So I remind people in my Calc 2 class, I tell them on a regular basis, I have a red phone at home. You don't want a red phone. When the red phone rings, right, you guys know the red button in Men in Black, right? That's, you don't want to push the red button. Well, I have a red phone. When the red phone rings, it's either the president or it's NASA. And it usually means, usually there's a meteor headed this way. It's only going to be here, a matter of hours, right? Bruce Willis and the boys from Armageddon, they're too busy to go up there and blow it up. So it's left to my calculus classes to find the answer. Then I send it back to, to NASA or whatever. And now they, have the right coordinates to launch the rockets to do all the dirty work. And if we don't find the answer, no one will know. We just won't all be here tomorrow, So on a regular basis, my calculus classes have to save the world. You don't know this because you're still here, but it happens all the time on a regular basis. Well, guess what? We're only minutes away from destruction. It's almost entering the atmosphere right now, the latest big old meteor and all that kind of stuff. We need to answer this, but there's no formula. It's a technique. We're going to do that. True or false? Now, what is the domain? This is not obvious. What is the domain of my x to the x power? Only positive numbers. Because if I do negative numbers, then most of your output will be imaginary. Everybody understand? So your domain is only positive numbers. So x to the x, right? 1 to the first power, 2 to the second, 3 to the third. This thing's growing really fast, isn't it? So one of the questions that I'm going to ask on another day, later on, we're going to ask, what's the limit as x approaches 0? Which is really cool because we can't actually physically do it, but I'll show you how to do stuff like that. This is the key. Go with me, right? If somebody walked in the classroom right now, is that terrifying? I got e to a function. Do you know how to differentiate that? I think you do. I'm pretty sure we can all do the derivative of that guy. So here's what I want to do. The derivative of x to the x is equal to the derivative of e to the x log x. And I'll do it long to write out all the steps. Well, what's the derivative of e to the thing? Isn't it e to the thing times the derivative of thing? Stare at that. Are you happy with that statement? Is that exactly what we did last day? The derivative of e to the thing is e to the thing times derivative of thing. But derivative of thing is just a simple product rule. That's not complicated at all. What's this derivative? First times derivative of second plus second times derivative of first, which is, bless you, 1. That's just x plus log x. And isn't this just e to the x? Or excuse me, x to the x? Isn't that where that came from? So what's our answer? The derivative of x to the x, this is x to the x.
Wait, were you getting that?
Oh, I'm sorry, this should be a 1.
Yeah.
Sorry. I need you guys to jump in faster. That's the answer. Very horrible, but that's the answer. How did we do it? The rule is that we know function to a power. Piece of cake. That's called the power rule. We know exponent to the function. That's what we've done the last 2 days. E to the x, a to the x in general. But I have function to the function. There is no formula for that. But there's a technique that if I have a function to the function power and I do the e to the log thing, then that exponent comes down and now it's just a simple product rule on my e. It doesn't matter what the question is, you would all be able to do that. Does that make sense? And this is what I mean when I say technique. Techniques are not functions, sorry, formulas. It's not, oh, here it is, so here's what the answer is always going to be. No, there's not going to be an always answer, but the technique allows me to get to a place where I can now use what I already know. Let's do another one. Let's use things we already know how to do. So let's suppose we have, let's take something truly nasty. How about if x to the log x. That just looks horrible, doesn't it? You all agree that's horrible? I think you all agree that's horrible. I'd like the derivative of this. I have no idea what the derivative looks like. But once again, the domain is only positive numbers. Well, is it true that this is e to the log of x to the log of x? But That's e to the log x
Square.
times log x. Would that be true? Might be easier if I do it that way. Question. Question. True or false?
False.
First one I'm squaring the log function, the second one I'm squaring the x. No, they're not even similar. Is that a mistake we sometimes make? Yeah, you know where we've been making that a lot lately? We've been doing this a lot lately. This is not true. It's not even a similar question. I'm squaring the sine function, I'm squaring the angle. No. So the first one, writing in parentheses, is the correct way to go. You could have wrote log x times log x and then use product rule. Might as well just write it as log to a power. It's less work. This is my original function. Haven't done any calculus yet. So dy dx is e to that times the derivative of log x to the second power. This is function to a power. So let's just do this part. It's function to a power, so what's the derivative?
2 natural log of x, 1 over x.
Times, and that would be the chain rule factor. That's it. If I had done this as a product rule, which would be correct, I'd had to write a lot more to get to the same place. Can I just write this as, this part here as 2 log x over x? Would that be legal? It'd be more efficient. I'd rather have just one quotient. So now, isn't this that? So can I say my answer is x raised to the log x times 2 log x over x? That's pretty horrible looking. Could I say that? I'm not sure I want to write that as one big quotient. I think it would be really hard to read. I think I'd rather write it as the original function times the other thing. But was that horrible and difficult? Once I knew the route, it wasn't actually that bad, was it? So function to the function power. That's the most evil, disgusting, awful derivative you'll ever take, and it's probably the one you will do least. It doesn't come up a lot. So it's not something you should, labor over and worry. But it can come up, and I want you to know how to deal with it. If it does, then we've just figured it out. That's it. It's actually not bad at all. Okay? Everybody cool? All right. We're going to take a break in a moment. When we come back, we're going to completely change gears. We're going to go in a very different direction. Go ahead and press the red. I got to do the roll still.